faithfully delivering value and interpreting great books from around the world. Hello, this is Sally's Book Talk. Today, the book we're interpreting for you is The Last 3 Minutes. Since ancient times, the origin of the universe has always been a mystery puzzling humanity. In 1965, American physicists Penzias and Wilson discovered the cosmic microwave background radiation, confirming we can still observe the aftermath of the Big Bang. Since then, the Big Bang theory has gradually gained public acceptance. In the book A Brief History of Time, physicist Stephen Hawking proposed that after the Big Bang, in far less than a second, the universe's radius increased by 100 trillion. 100 million times. Hawking's view pushed humanity's understanding of the universe's birth moment forward. As our grasp of the universe's origin deepens, our curiosity about how it will end grows stronger. Will it keep expanding, flourishing endlessly, or slowly decay, heading towards oblivion? What is the ultimate fate of the universe? Will it vanish forever? And then, what will happen to humanity? In the last 3 minutes, author Paul Davis will guide us in exploring how the universe approaches its end. This book has 11 chapters, roughly split into 3 parts. Part 1 covers the origin of the universe. Part 2 introduces key concepts in cosmology and physics needed to explore the universe's end. Part 3 presents different viewpoints on possible end-of-universe scenarios. Paul Davies is a professor at the University of Adelaide in Australia, a renowned physicist and popular science master. The Washington Times hailed him as the best popular science writer on both sides of the Atlantic. This interpretation will revolve around 2 big questions. First, what factors influence the fate of the universe? Second, what conjectures do scientists have about the universe's fate? Let's start with the first question. What factors affect the fate of the universe? Actually, the universe has 2 opposite trends, collapse and expansion. Its fate depends on their relative speeds. If expansion dominates, the universe will keep expanding forever. Conversely, if collapse takes over, after expanding for a while, the universe will contract and vanish into a singularity. To understand this, let's now discuss the factors affecting the universe's expansion and collapse. Let's talk about what cosmic expansion is all about. By exploring the universe's past, we can see that so far, the universe is actually in a continuous expansion process with strong evidence from the redshift phenomenon of galaxies. So-called redshift means that the spectrum of a star shifts towards red light, that is, towards lower frequency light waves. According to the Doppler effect, when an object moves away from an observer, the frequency of its emitted spectrum decreases. In other words, distant stars are moving away from us, and the universe is expanding. If the universe is expanding, then in the past it must have been in some compressed state. If we play time backwards, we'll see all galaxies converging together. Based on the current expansion rate, it would take billions of years for the scale of the universe to converge to 0. That is to say, the Big Bang happened billions of years ago, and it's the origin of space, time, matter, and energy. Through further research, scientists have found that the universe's expansion is not linear. The universe isn't expanding at a constant speed. In the first fraction of a second, the universe underwent inflation, meaning exponential high-speed expansion. This might be the result of anti-gravity. So-called anti-gravity is a hypothetical repulsive force opposite to gravity. Some research theories suggest that in the early universe, under extreme temperature and density conditions, anti-gravity could have existed. If the inflation theory is correct, then the universe took just 3 minutes to generate most of the matter, slowly aggregating into stars and galaxies, with the sun being one of them. I know that I am dead. Since the universe has been expanding all along, what factor causes the tendency to collapse? It's the omnipresent force of gravity. Next, let's use a supernova as an example to see the power of gravity. First, gravity makes stars what we see them as today. Inside a star, nuclear fusion reactions happen continuously. The product is a compressed gas that generates strong outward pressure, constantly resisting the inward gravity of the star's outer shell, forming a delicate balance that prevents the star from collapsing. Secondly, it's still gravity that leads the star to its doom. As nuclear fuel depletes, the star's inner regions stop producing heat, and thus gravity gradually gains the upper hand. Under gravity's pull, the star rapidly contracts until even atomic nuclei are crushed. At this density, a ping-pong ball-sized volume could hold nearly 1 trillion tons of matter. When gravity reaches its extreme, it faces an explosion. The collapse releases immense gravitational potential energy, creating a massive shockwave while emitting vast numbers of neutrinos. Neutrinos are elementary particles with no charge and extremely small mass. Then the star shines with the brightness of 10 billion suns for weeks. This is a supernova explosion, which doesn't completely destroy the star. Its core remains. If the stellar core is too small, say close to 1 solar mass, it becomes a neutron star. If the core mass is larger, it continues collapsing and ultimately vanishes into a black hole. This is the star's doom. Gas produced during aging stars' explosions becomes raw material for new generations of stars. But neutron stars, or black holes formed in this process, can't be recycled further. Like peeling an onion layer by layer, usable stellar material diminishes until exhausted. As stars gradually extinguish, the age of light ends forever. Eternal night follows, where gravity in black holes is so strong, even photons can't escape. When only neutron stars and black holes remain, 2 neutron stars merging may form a larger neutron star or black hole. When a neutron star and black hole merge, or 2 black holes merge, they inevitably form a black hole.
We've seen gravity is precisely what ends stars' lives.
Expanding our view beyond stars and black holes, considering gravity's effect on the entire universe, reveals insights about its ultimate fate. Will the universe end in expansion or collapse? This depends on expansion speed versus the universe's total gravity.
According to Big Bang Theory, if cosmic expansion is fast enough, it will overcome gravity and continue forever.
If expansion is too slow, gravity will prevail, halting expansion and triggering cosmic collapse.
The universe's ultimate catastrophe will then occur.
Let's examine how to calculate cosmic expansion speed and total gravity. Simply put, the universe's expansion speed can be determined by observing the redshift phenomenon. And, according to the law of universal gravitation, the total gravity of the universe depends on its total mass. If we could weigh the universe's total mass, then we could estimate its total gravitational force. However, measuring the universe's total mass is a challenging task. Some scientists believe we can derive the universe's mass by measuring the sun's mass. If we take the sun's mass as the average stellar mass, then by observing its gravitational effect on planetary orbits, we can measure the sun's mass. Then by estimating the total number of stars in the universe and multiplying by the sun's mass, we can estimate the entire universe's mass at about 10 to the 48th power tons. And calculated this way, the universe's total gravity isn't actually strong enough to compete with expansion. So we might conclude that if the universe's mass were only from stars, it would expand forever. But this estimation isn't reasonable because the universe contains many invisible objects, like dark matter, planets, black holes, etc. Plus, there's countless dust and gas, along with neutrinos and weakly interacting massive particles from the Big Bang, making the true cosmic mass much larger than estimated. By observing star motion speeds in the Milky Way, scientists believe there's abundant dark matter in our galaxy. So-called dark matter is theoretically invisible matter existing throughout the universe. It may be the main component of cosmic matter, yet it doesn't belong to any known matter that constitutes despair. Visible celestial bodies. Research on galaxy motion within clusters also proves dark matter's existence, affects their movement. So, how should we estimate dark matter's mass?
Einstein's general relativity predicts space-time distorts near massive objects, bending light passing nearby.
If a massive object lies directly between observer and light source, Bent light creates single or multiple images. Gravitational lensing. Through gravitational lensing, astronomers indirectly detect dark objects by observing changes in stellar brightness. However, different astronomers estimate the total amount of dark matter varies, ranging from 10 to 100 times the mass of visible matter in galaxies. So the key question is there enough dark matter to stop the universe's continuous expansion? Unfortunately, the minimum mass needed to halt the expansion is also within that 10 to 100 times range of visible matter mass. Therefore, I currently can't compare the universe's mass to this critical mass, so I can't determine if the universe will expand forever. To summarize, the universe began with a big bang and has been expanding ever since, and it might just keep expanding forever. Oh, well, and in the galaxies born from the universe, some stars evolve into black holes with immense gravity. So another possibility is that if the universe's matter mass is large enough, gravitational pull between things will curb the expansion and the universe might collapse under gravity's sway. Now, back to our second question. What guesses do scientists have about the fate of the universe? Based on different assumptions, Professor Davies paints different pictures of the universe's last 3 minutes. Next, we'll cover continued expansion, collapse, and rebound as the 3 possibilities. The first assumption is that the universe will expand forever, and during this, gravity will wage a long tug-of-war with the cosmos. The expanding universe tries to stretch distances between celestial bodies while gravity pulls them together. It's a compromise. Galaxy clusters stay bound and concentrated, but distances between galaxies grow farther apart. Gravity's energy radiation will slowly drain stars' energy over time, so dead stars will drift toward other dead stars or black holes, kicking off a grand feast of swallowing and merging. Take our solar system. Under gravity, in 100 trillion years, the sun's orbit around the galaxy center will shatter, and its remnants will slowly slide into the galactic core where a massive black hole awaits. Apart from black holes, some matter will linger in the universe, like neutron stars, rogue planets, and thin gases and dust. So will these survive forever? Let's first look at protons, the fundamental particles that make up all matter. Different theories predict different proton lifespans.
According to one theory, the average decay time for protons is 10 to the 28th power years. That's 10 billion times longer than the known age of the universe.
But this 10 to the 28 is the predicted average lifespan. With enough protons, one could decay right before your eyes. If protons do decay, and eventually all protons will disappear, neutrons won't escape either. Given enough time, white dwarfs, rocks, dust, comets, gas clouds, and all celestial bodies will perish. So the 10 to the 48 tons of ordinary matter we observe are doomed to either vanish into black holes or decay through slow proton or neutron decay.
Perhaps only decay products will remain. Isolated electrons and positrons, plus their annihilation products.
Photons. So the expanding universe's prospect looks like this. Big Bang's leftover photon or neutrino background radiation persists forever. As the universe expands, these particles' energy diminishes to negligible background, while all ordinary matter vanishes and black holes evaporate, leaving only electrons and positrons. This eternal death scroll of dark nothingness is the modern cosmology version of the 19th century's popular heat-death hypothesis. Its cause fortunately, cosmic degeneration takes unimaginably long, but will all life forms ultimately perish? How will humanity face this? Comfortingly, Earth will support human habitat for 2 to 3 billion more years. Humanity's first challenge is the solar system's demise. So, we'll develop interstellar migration tech, expanding from Earth to other galactic systems. But what will these human migrants become? Perhaps they'll genetically modify themselves to adapt to different planetary environments. Physically and mentally, Future humans needn't resemble us. They might not even be organic, possibly becoming hybrid symbionts of organic and artificial neural networks. So, in the future, the boundaries between biological and non-biological, natural and artificial, human brain and computer will become increasingly blurred. Humans might even appoint artificial agents to explore places unsuitable for human expansion. However, no matter how advanced technology gets, human descendants will still be constrained by the fundamental laws of physics. The threat they face comes from the continuous depletion of available energy in the universe. Information processing consumes energy, and all intelligent beings will ultimately face an energy crisis. Actually, if intelligent beings want to extend their lifespan, they have two paths. One is to survive as long as possible. The other is to speed up the rate of thinking and experiencing. The faster a person processes information, the more thoughts and feelings they generate in a given time. Thus, their subjective experience of time passing becomes faster. Considering the limited energy in an expanding universe and infinite time, humans need to adopt a balanced strategy between information processing and hibernation. Facing the universe's energy crisis. By conserving resources and hibernating at appropriate times, humans could still achieve a near immortal subjective experience. All these speculations are based on the premise that the universe will expand forever. But according to a second hypothesis, if the universe someday stops expanding and begins contracting, what changes would occur in the fate of all things?
If the universe is destined to contract, then its end would be a different scenario.
When the universe begins contracting after reaching its maximum size, once it shrinks to our current universe's size, the collapse speed will accelerate. Because the universe doesn't expand at a constant speed, and conversely, it doesn't contract at a constant speed either. Continuous forces during collapse will make it an accelerating process, and the denser the matter, the stronger the gravity. Well,
In the next 10 billion years, the continuous rise of cosmic microwave background radiation will increase the temperature.
when the temperature rises to 300 Kelvin, which is about 27 degrees Celsius, Earth will start being unable to dissipate heat outward. The greenhouse effect will make Earth hotter, and human descendants will have nowhere to go. Afterward, every few million years, the universe's scale will halve, and eventually, the cosmic microwave background radiation will become so intense that it shows an ominous dark red glow in the night sky. As changes accelerate, things become increasingly extreme. Noticeable cosmic shifts now occur in just 100,000 years, then 1,000, then 100. During this acceleration, temperatures will soar to millions, then billions of Kelvin, compressing space and matter infinitely. Space that once held an entire galaxy will shrink to a diameter of mere light years. The universe's last 3 minutes arrive. Atomic nuclei disintegrate, reducing matter to a homogeneous soup of elementary particles. Ominous pause.
All structures except black holes vanish, a process taking near seconds.
Next, matter undergoes intense compression. Since protons and neutrons consist of quarks, crushing them leaves a quark soup. Microseconds before the ultimate end, black holes begin merging. In the final moments, gravity dominates all inward collapse, a converging shockwave called implosion. It will crush all matter, space, and time itself at the singularity, the universe's end. For humans, subjective time depends on metabolic rates and information processing speed. If remaining time can be infinitely extended in the mind, we needn't fear time's end.
Humans can accelerate thinking to counter the approaching apocalypse.
With enough energy, we can buy time. And in a collapsing universe, releasing energy is never the issue. So far, we've assumed the end is far future, but we must consider another possibility. Human cosmic understanding is light speed limited. If the sun exploded now, we'd know only after 8 minutes 30 seconds. Similarly, a nearby star could have gone supernova, bathing us in lethal radiation without warning. And while bad news travels at light speed across the galaxy, we remain unaware until it arrives. This phenomenon is called the past light cone. In quantum physics, vacuum states differ by energy levels. True vacuum and false vacuum. True vacuum has the lowest energy level or ground state. False vacuum is a theoretical concept. Its energy level is higher than true vacuum, containing enormous energy and being extremely unstable, ready to decay into true vacuum state at any moment. One theory suggests our universe might not be in a stable true vacuum state as we assume, but in a fragile, false vacuum state. If vacuum decay occurs somewhere, it may transition to a lower energy state, triggering terrifying consequences.
Regions bordering true vacuum would collapse into a space-time singularity in under a microsecond,
Annihilating everything instantly.
terrifyingly. Due to the past light cone effect we mentioned, we wouldn't know where vacuum bubbles form before they expand at light speed, giving no warning. Death strikes suddenly.
Yet, paradoxically, vacuum bubbles might be cosmic inhabitants' only escape route. From true vacuum's perspective, the false vacuum bubble region resembles a black hole. As connecting wormholes pinch off, it separates into a new baby universe. This way, new universes might be born in batches. Each universe undergoes birth, evolution, and death, but collectively, they exist eternally. We don't know if baby universes inherit physics from parents or undergo Darwinian-like evolution between universes. But comfortingly, when a universe's last 3 minutes come, conscious life might survive elsewhere. These aren't our only escapes. Even collapse doesn't mean complete annihilation. A third hypothesis proposes cosmic rebound, starting new expansion-collapse cycles. Thus, the universe would have no true beginning or end. This closely resembles the Buddhist concept of reincarnation. The cyclical model offers comfort, each rebirth like a phoenix, evolving new structures and systems. But this theory has flaws, requiring rebound at extreme densities during late collapse. Moreover, certain physical processes disrupt the symmetry of each expansion-collapse cycle, leading to unavoidable consequences. One consequence is each cycle produces more black holes than before, making perfect cyclical repetition impossible. Like a balloon repeatedly inflated and deflated, after several cycles, it may never return to original size. This concludes humanity's exploration of the universe's end. Since its birth, does the universe's journey have an end point? If the universe had a purpose and fulfilled it, then it must end, because continued existence would become purposeless and meaningless. Conversely, eternal existence implies no ultimate cosmic purpose. If the journey has no destination, does it still hold meaning? Perhaps when the universe reaches its final 3 minutes, human descendants will discover its true meaning. Well, that concludes our interpretation of the last 3 minutes. Find the reading notes below the audio. We'll see you next time.